In this video, we're going to look at the queue abstract data type, which is quite similar to the stack abstract data type in terms of how it's implemented and how it can work, but is a different kind of data type and is used in different settings. Okay, so a queue is meant to represent exactly what we think of as a queue or a line, right? Things that are inserted at the end of a queue and removed from the front. Like when you get to the grocery store, you get in the back of the line, and then they work through everyone who's ahead of you, and then eventually it's your turn when everyone ahead of you is done checking out, for example. Or a drive-through line at a restaurant. These are all queues. So you insert at the back and you remove at the front. So for example, if I push A, then there's nothing in my queue, then A is both the front and the back. But then if B arrives and I push B, B gets added to the end. And then if Z arrives and we push Z, then Z gets added to the end. And then when we pop something, we pop the front, in this case A, and then we'd pop B, and then we'd pop Z. We have very similar interfaces for a queue as we do for a stack. So when we want to add something to a queue, we call it a push, and we're always going to add it to the end. When we want to remove something from the queue, we call it a pop, and we're going to remove from the front of the queue. Removing, again, just like for the stack, when we remove, we don't necessarily get a copy of the thing we remove. So if we want a copy of it, we use the peek function to ask for the thing at the front of the queue. Empty tells us if the queue is empty, and then size tells us how many things are currently in the queue. Now, an example of where you might use a queue might be in some sort of server that's accepting requests over the internet and then processing them in the order in which they're received. This could be like an Amazon server in which somebody's placing orders, and then if your order goes in first, you get the item, and if you get the last one, then whoever's order arrived after you, they don't get that item, and they get notified that it's sold out. Right, so this kind of queue-based processing has a kind of fairness to it that most people, like. And so the way this code might work, again, this is pseudocode, not C++. Our server might receive a request and then push it into their queue and acknowledge that they received the request. And then if the queue is not empty and if the server is available to service the request, it gets the front of the queue, tries to complete the request, and then if it succeeds in completing the request, it pops it. Something along these lines. Now, obviously, it might need to pop it no matter what at some point, but this is just to give you an idea of how this could work. So you just keep accepting requests as they come in, you stick it in your queue, and then you process the oldest request. This is kind of a very common way you might handle some sort of server-based application. We can implement a queue using a list. Shouldn't come as a big surprise. We could implement a stack using a list, and operations are very similar, and so we can implement a queue using a list. Push is the same as inserting at the tail, and pop is the same as removing at the head. And we have support for both of these on our list class. Okay, so our queue abstract data type might look something like this. We have a list inside of it that we keep private so that no one else can muck around with and perform an operation we don't want to have happen on a queue. All right, like insert in the middle. And then we create our interface that has the push, the pop, the peek, and the empty. Okay, and we can put all this in a header file we call queue.h, and then we can include queue.h whenever we need a queue. Okay, our push function will take an item and push it to the end of the queue. And so for that, the simplest thing to do is to use a pin. And we just write list.append item, and this adds the item that was passed in to the end of the list inside this object. And then pop is basically the same thing as our stack code, because when we remove, we want to remove from the head. And so we just pass in a null iterator into remove after, and that's going to remove the head for us. So push adds to the end, pop removes from the head. And then for peek, this peek should remove the item at the head of the list. And so this is the same code as we had in stack. We just have an iterator that's pointing to the beginning of the list, and then we return that item. It's worth noting we shouldn't do this on an empty list. If we try to do a peek on an empty list, that's going to cause problems for us because we're going to basically dereference a null pointer here. So we shouldn't do that. We should always check to make sure the list isn't empty if we're not sure. And so, so the empty function is just asks the list if it's empty and returns that result. This implementation is pretty efficient because the list itself is efficient, right? Inserting an element into a list, we can do that in constant time, so that means push is constant time. And removing an element from our list is constant time, so that means pop will be constant time. And pulling the front from a list and returning it is constant, so that means peek would be constant. And empty is easy and fast because we're just checking if the head of the list is null. So that's also O1. And then checking the size, we didn't implement that, but all you need is a counter, and every time you push, you increment it, and every time you pop, you decrement it. And so those would be very simple operations that would also be constant time. So the time complexity of our linked list is of our queue-based implementation, of our linked list-based implementation of our queue, sorry, stumbled on my words a little bit, is all very efficient because our underlying list is efficient. Okay, so in summary, queues order data in a first in, first out manner and typically support push and pop operations. Queues have efficient implementations using singly linked lists. Queues can also be implemented efficiently using an array. And this is, especially if you have a queue in something like hardware, inside processors, we often implement queues a lot for various purposes. And there, that's fundamentally a buffer, it's fundamentally an array. And so you should be aware that a very common way to implement a queue is just using an array. And it can achieve similar efficiency on an array as it can with the list. We're going to find it very helpful to have a data type like a queue as we implement other data structures. Queues are going to help us, especially when we are traversing trees and traversing graphs. And we're just going to need to reach for a queue and use it on occasion. Same with a stack. Okay, so these data types will be handy as we go along. They're pretty simple to understand. They're intuitive because we have experience with these sorts of data, these sorts of things in our daily life, right? But they're gonna show up again and again as we implement other data structures. They're going to be a helpful part of implementing more sophisticated data structures.